In this tutorial, we're going to look at the phenomenon of diffraction. Diffraction is a very important phenomenon. It's not as well known as others, but it explains two very important concepts amongst others. The first relates to the little demonstration I did in the class before, where I was hiding behind a board and you couldn't see me, but you could hear me. We didn't explain why that was. This will be the phenomenon that does it. So, long story short with that is the reason you can hear me is because the waves that are coming from the sound waves are bending around the barrier, whereas light waves coming from me cannot bend around it. And so when waves bend around a barrier, and there's an alternative to that, they are said to diffract. So we're going to learn what it means to diffract, why it diffracts, and what the criterion for diffraction is in this lesson, and then a little bit of application. The second major application of diffraction that we want to talk about a little bit will be the concept of resolution, the ability to see an image sharply. So let's start with a very important principle. It's kind of abstract, but it's key to understanding why diffraction occurs as well as other things. And it's called Huygens principle. Christian Huygens was a Dutch physicist contemporary of Isaac Newton, and he was at the time the expert on waves. He developed many ideas and models that we still use today. So let's take a look at this pictorially before we describe it. Okay, so let's take a look at a wavefront as designated by this wavefront right here, which is a plane wave. And we said that a moment later it will look like a plane wave there. So how does that form? Well, Huygens came up with a very interesting idea. He said there are an infinite number of points along this wavefront, and I'm highlighting some of those, but in the diagram there are 3. He says each little point acts like a source of waves that propagates out like concentric circles. So if I have a little point here, it will, a moment later, propagate out as if it's a new source of waves out in front of the wavefront, and this one will propagate outward and create a little wavelet out in front. So the first thing says every point on a wave front acts as a tiny source of wavelets. And they propagate out in the forward direction at the same speed as the wave itself. So this point creates a wavelet, this point creates a wavelet, etc. And I could draw in many others between and beyond those, but 3 is sufficient here. Okay, so those wavelets will show when the next cycle later what the wavefront's going to look like. So we have these 3 wavelets, and how we draw the wavefront, it basically comes from the superposition of all those wavelets. And when you do the superposition of them, the shorthand way of doing that is nothing more than a tangent to all the wavelets. So this line right here is touching the tangent of all those because of the superposition, and sure enough, we get a full cycle later another parallel wave. And so if we start from here and do where the next wave front is going to look like, so I'm going to choose 3 random points. You don't have to draw this, pay attention, and I do a wavelet that has the same wavelength as before, because we're traveling at the same speed, so for a given time it's going to cover the same distance, then my new wave is going to be parallel to that, and sure enough, I've got a parallel wave. And if we look at this from a circular wave front, in other words, we're close to the source, so let's say our source is right here. After one cycle, we have a wave front that looks like this, at least to the right. If I want to draw the next wave front, I choose some points as my wavelets, those black dots that I'm highlighting now, and I draw their corresponding wavelets. And if I draw a tangent to them, I get this wavefront, and sure enough, I've got an equally spaced circular wave. And if I do it again, and I'm not going to do it fully, but if I want to draw what the next wave looks like, which we kind of know what it's going to be, I draw a wavelet, a wavelet, a wavelet, equidistance, and then I draw a tangent to all those. Then I can start developing those wavefronts. Okay, so that's pretty important. So really, this propagation of wavefronts is ultimately an interference effect. So how does this lead to the phenomenon of diffraction? So when wavefronts encounter barriers, okay, or they pass through an aperture, which is an opening between barriers, they can do one of 2 things. They can bend around the barrier, or they can spread out through the aperture. Okay, so that's a very important manifestation of diffraction. So let's explain those a little bit more pictorially and then conceptually. So I have a wavefront coming in parallel, and then I hit the barrier right here. Now, common sense would suggest that the part that hits the barrier is stopped, and then the rest would just propagate on in the forward direction, staying parallel and equally spaced, even though not doing a very good job. But that's not what happens. We see that it's kind of leaks around the edges behind the barrier. That's diffraction. So why does that occur? And then secondly, we can see it in this opening in the second diagram. I have wavefronts with all their little wavelets propagating forward. And one, again, might think that when it passes through, they would just go through and stay like this beyond it where the gap was. Yet we can see here that they fill in behind the gaps, behind the barriers, which is a demonstration of diffraction, and we want to understand that. So how do we understand that? Well, the simplest way to, in my opinion, do is you got to remember that these wavefronts are an interference phenomenon. So when we get, if we look at, let's say I'm back to the diagram on the left, all the wavelets that are away from the barrier are interfering with each other, so they maintain that nice parallel front. But the wavelets that are near the edges, they don't have a neighboring one, at least on this side, to interfere with it. So the wavelets start taking on a circular shape, and so they fill in. So it'll look like this. And so they're bending, if you will, around the barrier. And with the opening, right, we have a parallel here, but now they start to bend around because there's nothing on either edge to interfere with it to kind of maintain the status quo. That's a little bit abstract, but if you look at the diagram enough and the next statement, hopefully it will come together. So the edges, there are no adjacent wavelets to interfere with their neighbors. So a plane wave, which is initially what's coming in, becomes more circular at the edges. And the longer you go on, the more it becomes circular and circular. Okay, so let's now, and here is a classic example of this. So here is Lake Ontario. Looking from above, you can kind of see that many of the waves coming in are plane waves, right? And then here is an opening right there. There's a breach in a wall, barrier, I'm not sure what exactly it is, because of flooding. So let me erase that, and if you look very closely here, you will see diffraction going on. The waves are spreading out, and they should be equal wavelength. And so we have a very, very nice picture of diffraction. So let's formalize that study a little bit more. Okay, so wrong page. So let's define diffraction formally. Tendency of a wave to spread out. Remind me to show you a little simple laser pointer demonstration. It happens with light, it happens with sound, it happens with ripples and ponds, it happens with all waves. As a consequence of this, when a source of waves encounters a barrier, they will bend around it, as we mentioned earlier, or when they encounter an aperture, they will spread out as if the opening was a new source of waves. So let's take one of these at a time. Let's go to the bending around a barrier. So in this diagram right here, we have plane waves coming in, and then we hit a barrier. Notice that they stay plane waves away from the barrier, but then they start bending around it, and they eventually join right around here. There is a shadow area behind that barrier, okay, but the waves will eventually fill it in, and if we could go on long enough, it would look like a plane wave again. Because, again, the edge ones don't have neighboring wavelets interfere with it, so they're free to become more circular. Notice in the second diagram, we have the same waves coming in, but our barrier is smaller. If you look at what happens after, you'll see that we have diffraction again, but the diffraction is more noticeable. In other words, it takes fewer cycles before it's completely joined again right here, and so we cast a much smaller shadow. We want to understand what the relationship is between the wave and the barrier, such that you get a lot of diffraction or a little bit of diffraction. And we see something similar here with the aperture. So here I have plane waves coming in, and then I have a very wide opening. And if I look at the amount of diffraction, it's there, but it's moderate. It's not very pronounced. It takes a while for it to really start spreading out behind these barriers. If I look at the second situation, I have a very small opening, and my diffraction is very noticeable. Okay, it fills in right behind the barrier as if it's not there. So this is an example of shining a light through a doorway where the light would just go more or less straight ahead with very little diffraction. So if I'm sitting here, I would not see any of that light. Whereas if it was with sound and someone was speaking or a speaker, because of the properties of the sound, which I'll explain in a second, they will fill in the whole room so I can hear it even though I'm not directly in front of the aperture. So what are the criteria for the amount of diffraction? Okay. So in either case, the amount of spreading or bending, or i.e. diffraction, depends on two things. A, the size of the barrier or aperture, depending on the situation, and a certain property of the wave. If you haven't figured out by now from the diagrams, it is the wavelength, and the wavelength only, not the amplitude, not the velocity. Okay, so here are three criteria. If the wavelength of the wave is much smaller, that's what those two less than signs means, much smaller than the barrier or opening, then diffraction is minimal. And this is what happens with light in the case of me standing behind the board or the whiteboard. Is the light coming from me has wavelengths that are on the order of nanometers. The board is on the order of a meter, so that's tiny compared to the size of the barrier, so it does not bend around. If the wavelength is approximately the same or the same order of magnitude as the barrier opening, and that's what the case was with sound. Sound waves have a much longer wavelength than light waves in general. Then the diffraction is moderate. And the most important case I want to look at most is if the wavelength is much greater than the barrier. In other words, you've got a huge wavelength compared to the barrier opening, the diffraction is significant. And we'll look at some examples in class. So to finish up here in a few minutes we have remaining, why should we care about waves diffract? I'm just going to give you two major examples. First, one we already talked about, explains why we can hear but not see around corners. So let me reiterate. When you talk, your sound waves have wavelengths on the order of centimeters to meters. Light waves are on the order of hundreds of nanometers. So when I put that board in front of me, the wavelengths of sound are roughly the same size as the barrier, so they will diffract around it fairly readily. Light cannot diffract around it. If I were standing in a doorway talking, again, the width of the door is is roughly the same size as the wavelength, so they'll fill it in, whereas light is tiny compared to that opening, so they do not diffract around it. The second and more important case is it explains resolution issues. And I'll show you some slides tomorrow. I'll remind me to do that. Resolution is how sharp an object appears. For example, we can never ever see atoms, and with light microscopes we can never clearly see certain microorganisms like viruses and that, or structures in the cell. And I'll go into more detail in class, but let me just give you the short answer here. So why is it there's a limit to the resolution, what we can see with a microscope? It has nothing to do with the microscope itself. It has to do with light. In order to see an object sharply, let's say the nucleus of a cell, you have to have light hit it, bounce off, and then come through the lenses, be magnified, and you get a sharp image. But since the nucleus of the cell is so small, or the chromosomes therein, the wavelengths of light that hit it are actually longer, wavelength-wise, than the size of the object. And so because the wavelength of visible light is larger than the objects, or at least roughly the same size, okay, the light will diffract around it. And because it diffracts around it, it does not cast a sharp shadow. In other words, the object you're looking at will be very, very fuzzy. So it doesn't matter what the magnification is of your microscope based on the lensing. The fact that you're shining light of a particular wavelength on objects smaller than it means you can never get a sharp image of it. So there is a partial solution. We can get around it a little bit by using the wave properties of electrons. That's something we'll talk about later on, because electrons we usually don't associate with having wavelength. But they have a much shorter wavelength, therefore we can see much smaller objects with high resolution. Okay. And the last thing, this is a technology that's becoming outdated, but it's still around. It determines the limit of information that can be stored on a CD or a DVD. Okay, you can only put so much information on those because you can the little pits in there that store the information are so close that diffractive effects make it impossible to resolve the digital information. All right, so we can't distinguish one little bit of information from another when they're too close together, because what reads them is a laser light, which laser light has a certain wavelength, and if the wavelength is on the order of the separation between the two pieces of digital information, we can't tell them apart. Okay, so we'll do mathematical aspects of diffraction next. Come in with questions if you have any about the conceptual. You can try the problems on the back of this. There's 4 conceptual problems, and we'll talk about them in class.